Okay, so in the last session we have created kinds of problem the distribution. So I'll write it in an easy way to make you understand now. So this is balls versus uh, urns, and so this can be written into four ways. So let's say II, which are identical, ID, DI, and D. So this is distinct and identical, distinct, right? We have again this table. So we have here that there is no restriction. So we write it as NR. Then not more than one ball in a urn. So not more than one, and MO, let's say. No urn is empty. No urn empty, NUE. And finally exactly one ball in the each and every urn. So this is a bijection, so we'll say ball bijection between urn and the balls, BUB. Okay, so these are the 16 kind of problems which you can see, right? So let's try to fill this table with the various ways we can do it and what are the methods and techniques used. So let's take the most easiest one, which is each and every ball has one urn, right? So this is the bijection between urn and the ball. So each urn will contain exactly one ball, right? So let's try to figure it out how we can, find those. So this is our problem statement. So the number of distribution of n balls into k urns in which each urn must exactly receive one ball is given by 0 when so there is a mistake here, I'll just correct it for you, when n is not equal to k. N is not equal to k. 1 when n is equal to k and either the balls or the urns are identical. Factorial n when n is equal to k and both the balls and urns are distinct, right? So let's try to see how we achieve at this. So when n is not equal to k, so when let's take an example when n is not equal to k, n is not equal to k, right? So we have to do the bijection, right? So each urn should have a ball and each ball should be in a urn, right? Since there is a bijection and there are the balls are more and urns are less, or the urns are more and balls are less, so there is no possibility that we can distribute it like that. So henceforth it will be 0, right? 1 when n is equal to k and either the balls or urns are identical. So we say that there are n balls and there are we say that there are 5 balls and 5 urns, right? So for example, we have 5 balls and 5 urns. So each ball should be in the urn and each urn should have a ball, meaning by, so we have like 5 balls which can be placed into different urns. So each ball has one urn. So there is only one possibility, right? And here the condition is that either the balls or urns are identical. So if the balls are identical, then you don't need to arrange them. If the urns are identical, then you don't need to arrange them, right? So there is no arrangement problem. It's just like finding a simple combination. So henceforth there is only one way, right? Now, if both the balls and urns are distinct, they are not identical, then in that case, for each ball, let's say 5 balls, how many ways you can choose the urns, right? So the first ball can go into 5 distinct urns. Now, all the balls are different, so this is again by the multiplication principle, that will be factorial n or factorial 5. So these are the various parts which we have covered. Now let's try to fill this into this part. So we have identical, could be 0, 0. So we can simply write it here. 0, 0 when n not equal to k, right? And 1 when n is equal to k. Similarly, when either of the balls or the urns are identical, then similarly same thing, 0 when not equal to k and 1 when n equal to k. Same thing applies here, 0, 1 and not equal to k and n equal to k. And when they are distinct, of course, and they are equal, right? So we can put a remarks here. If n not equal to k, then it's 0, and if n is equal to k, then it's factorial n. So this is one of the easiest part of the distributing the various balls into the urns, when exactly each ball, each urn should contain exactly one ball. So there is a bijection and none of the urn can be empty, right? So this is one of the problems. So we will move in the next session the other kinds of distribution problems.